Hello, and today we're going to talk about gravity. It's a really exciting thing because generally the law of gravity is strictly enforced. What is gravity? Actually, gravity might not be quite exactly what you have perceived it to be. It is simply the attractive force that acts on all objects that have mass. We're going to talk more about that. These are some things we're talking about in this section. What is gravity? Is it the same everywhere? What's a gravitational field? And are weight and mass the same thing? So we're going to start talking about the law of universal gravitation, but I'd like to just talk a little bit about Isaac Newton. You've heard his name. These are the years that he lived. He was really amazing. He invented calculus in order to help him explain his laws of motion. He wrote the Principia, Mathematical Principles of Natural Philosophy is what the whole title translated into English is, where he described these famous laws of motion, and that's what we're gonna learn about in this unit. But I kind of wanted to give you an idea of the fact that his life didn't really start out all that perfect. You might think, wow, somebody that accomplished those great things must have had a tremendous advantage. His father died 3 months before he was even born, and he was born very, very prematurely. And then when he was 3 years old, his mother left him to be raised by his grandmother, and she went and remarried, and he had a very hateful relationship with his stepfather. Wasn't a good thing. He really didn't like the man at all. And his mother's always trying to get him to be a farmer, and he never really took to farming much. So he had a lot of struggles in his life, and ended up doing some really great things despite some of that. The universal law of gravitation that he came up with, it was a new idea at the time. It's the gravitational force between two objects. And it depends on two things: their mass and the distance between them. So let's take apart these two factors that affect the force of gravity: the mass and the distance. We have a really large mass and then a smaller mass. We're going to have some attractive force between them, right? If we reduce this really large mass to something smaller, the force of gravity is going to be less. There will be less pull between them. And you kind of know this probably from just studying things in space. The sun exerts a tremendous force on the Earth because of its mass. But distance matters too, not just size. So if distance matters, we know that if two objects are pretty close together, there's going to be a much greater force of gravity between them as opposed to farther apart. And that's why the moon actually is exerting, even though it's so much smaller than the sun, it's really close. And so its gravitational pull definitely affects the Earth. And you know that because of the tides and things like that you've studied before. Okay, so here is the formula. And formulas are so nice and convenient because instead of lots and lots of words explaining these ideas, it can be explained in a very simple format right here. And here it is. I'm going to tell you what each of these symbols mean. The variable capital F stands for force. So the force, when we're talking about the law of universal gravitation, the force is going to be equal to this big G. What is that? Well, it is the universal gravitational constant, some constant number that you'd be given. And we have, let's look at the masses. The masses of the two objects, because remember, the force is going to depend on the masses of them. So we have mass subscript 1, so that would be the mass of the first object, times the mass subscript 2 of the second object. Those are their masses. And d squared would be the distance between the very centers of those two masses. So when you look at the mass of the Earth you pretend it's just a pinpoint and you look at the very center of where the Earth is, and that's where you're measuring for any object. You're measuring to the very center of it. So here's some questions for you to ponder. Why is it that you are feeling the Earth's gravity, but you're not falling into the sun? After all, it's a lot bigger, isn't it? Well, remember our formula? The distance, the relationship for distance is squared. So distance really matters, and the sun is really far away. So because it's so far away, you don't feel the pull of that. The Earth certainly does, is feeling the pull, but you're not falling into the sun. You're falling into the Earth because you're really close to the Earth. Another question, why don't you feel the gravitational attraction of your pencil or even your car? Well, pause the video. Think about that for a minute. Maybe you can come up with the answer, and then you can start the video again, see if you get it right. Well, your pencil has very, 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 very little mass compared to the Earth, right? Even your car has very, 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 very little mass compared to the Earth. So remember, the force between the two objects is going to be dependent on multiplying their masses together and then dividing by the distance squared between them. So the mass really matters, and the Earth has a huge amount of mass. Your pencil and your car, they don't have much mass compared to the Earth. So we know that something has to have enough mass and a small enough distance to be affected by the force of gravity. Gravity, though, is a long-range force, and the gravitational force between two objects never actually disappears. It gets really, really faint and really small, but it never really disappears. If you think about two objects, say being 1 meter apart, hypothetically, there would be some force being exerted. Think about our equation that force is going to be proportional to 1 over distance squared, okay? And if we say 1 meter squared, we have a force of something like 1. What if we increase that distance, we double it and increase it to 2 meters? There's not much difference in the distance, but the force now would be proportional to 1 over 2 squared, which is 4. So we suddenly diminished the force by 1/4, just simply by doubling our distance. So every time you increase the distance, you're dramatically reducing the amount of force between the two objects. However, it never actually disappears. Even if the objects are very, very far away, there would be a minuscule amount of force but that is being exerted because gravity is a long-range force. Now let's talk a little bit about a gravitational field. First, when we talk about a field in science, it's not the football field outside. A field means a region of space that has a physical quantity at every point in it, like a force. We can have a force field. All objects have a gravitational field because at every point in the physical space, there is a quantity for that force. Since all objects have a gravitational field around them, certainly Earth does as well, and very near the Earth's surface, the strength of that gravitational field is 9.81 newtons per kilogram. So if for every kilogram that an object has mass, it will experience 9.81 newtons in that gravitational field very near the Earth's surface. This gravitational field, we'll just call it little g, that gravitational field decreases when you travel farther away from the Earth's surface because, of course, your distance is increasing. This little g is going to be very different very near the surface of the moon or very near the surface of some other planet because those objects have different mass than the Earth. Now, that brings us to another idea here. and you probably learned this before, but weight is not the same thing as mass. Mass measures the amount of matter that an object contains. It's how much stuff is there. Weight is actually a measure of the gravitational force that's being exerted on an object. So when you stand on your scale, you're measuring your weight, or how much gravity is pulling on you. So in the case of units, how do we think about this? Well, weight is a force, and force has units of newtons. Big N stands for newtons. Remember that a newton is equal to 1 kilogram times meter per second squared. Kilogram meter per second squared is a newton. And that's what force is measured in. So weight could be measured in newtons. We use pounds in the non-SI units to indicate weight. Weight on the moon is going to be different because it's a force. We're talking about the force, and if you're 560 newtons on Earth, you're going to be 90 newtons on the moon. What is your mass measured in? Always kilograms. Mass is always measured in kilograms. So that brings us to another really important equation, and that is our weight equation, or the force equation when we're talking about weight. The force of weight, F, the force of our weight due to gravity is going to be equal to our mass times the gravitational strength. So on Earth, you remember the gravitational strength is 9.81 meters per second squared. Mass, we measure that in kilograms. That's the little m. And F, with a subscript of g, is the force due to gravity, and that will always be measured in newtons. This g is going to be in meters per second squared. Earlier, you saw that 1 newton is 1 kilogram meter per second squared. That should be a superscript, sorry about that. And before we said that this gravity, this factor of gravity, was measured in newton per kilogram. And if you do the algebra and you substitute in a newton per kilogram, you're going to see that this works out to be the same, whether you call it a newton per kilogram or whether you measure g in simply meters per second squared, because a newton per kilogram is going to have the kilograms cancel out, and you're going to end up with just a meter per second squared anyway. So those are the same. So this is the equation that you want to remember and be able to use. Let's do an example. On Earth, what is the weight of a large screen TV that has a mass of 75 kilograms? So let's write our formula down that we know. We know the force due to gravity is equal to the mass times g, little g. Now, what other things do I know? I also know my mass because it's been given to me in the problem, 75 kilograms right here. I know g because it's for when I'm on Earth, g is 9.8 meters per second squared, or 9.8 newton per kilogram. And this may be easier for you when you work this problem to put it in newton per kilogram. Both of them are correct. So now, what am I going to do with my problem? I'm going to plug these values in because the thing I don't know this. That's my question mark, right? The force due to gravity is a big question mark, and that's what the question's asking. What is the weight? The weight is that force of gravity. So let's plug these values in. So when I plug these values in, I'm just taking this equation, I'm plugging values in. I'm going to say the force of gravity here equals my mass, there, 75 kilograms, times g, 9.8. I'm going to use the newtons per kilogram. And you can see that the kilograms cancel, This is on the bottom, this is on the top. And when I say 75 times 9.8, I get 735 what? What unit do I have left? Newtons. That's what I have left. So, on Earth, the weight of a large screen TV with a mass of 75 kilograms is 735 newtons. Some advanced ideas. What is the gravitational strength on the moon or on other planets? What would your weight be on the moon or on another planet? Figure that out. If you're interested in history, another advanced idea would be look up more about Isaac Newton, his life and things that happened to him and things that he discovered. And he definitely did a lot more than probably what we'll present here. So research that a little bit. That's very interesting. Also, you could research more about what happens to our astronauts when they spend time in low gravitational fields. What are some of the problems that they encounter? So I look forward to seeing you in class and seeing what you come up with.